To natChat, with today's topic being an innovative one, artificial intelligence in neurotechnology. This speaker series is hosted by Neurotech, the leading and most prominent neurotechnology innovator network in all of Alberta, with our main goal to promote innovation, collaboration, and education in the neurotech space. We hope you look forward to this event and our future ventures that will give everyone an opportunity to get exclusive talks from industry professionals, connect with others to expand your networks, and a chance to win free merch. I would like to extend an apology to everyone as one of our graduate speakers were not able to make it today. Nonetheless, we shall proceed today's series event with this presentation first by Mr. Harrison Fah, and then by Dr. Alex Murphy. After the speakers have finished, we shall open the floor to networking and provide food and refreshments to everyone. Our first speaker is Mr. Harrison Fah, who is pursuing his master's in computing science at the University of Alberta and focusing his research towards using machine learning to help identify risks and protective measures in neurodegenerative diseases. Harrison's intense passion for neurotechnology makes him a significant contributor in the field of computing science. I would like to welcome Mr. Harrison Fah to talk about some of his projects.
My slides? Are they on here? Okay. All right. That's okay.
Is that fine?
Yeah. Okay, cool. Okay, is the mic working fine? Yes? Okay. Hello everyone, I'm Harrison. I'm a third-year master's student here at the University of Alberta in computing science. Like they said, my research mainly focuses on using machine learning for problems related to Alzheimer's disease. But instead today I'm going to be talking about two different projects that I've worked on that involve both AI and neurotechnology. The first one's called Hecatron, and it uses reinforcement learning with EEG signals. And then the second project is called fMRI-CLIP, and it uses contrastive learning with fMRI signals. So the first project, Hecatron, I did this in collaboration with Nicholas Mellon and Harrison Kumar with support from Neurotech, as it was a Neurotech project. So the original goal of the project was that we wanted to develop and program a prosthetic hand that could be controlled purely through EEG signals. So we had this 3D printed prosthetic hand that each of the 4 fingers was connected to a wire, and then the wire would connect to a motor. And we wanted to write a program and have an AI that could detect when the user wanted to close the hand or open the hand based on their EEG signals. However, what we ended up making was just a general reinforcement learning framework for associating EEG signals with any action. So first off, what is EEG? So EEG stands for electroencephalogram, and it refers to recording electrical activity within the brain. On the right in these pictures, I'm wearing 2 different EEG headsets that are within the Neurotech office, the OpenBCI on the left and the Muse headset on the right. These signals can then be used to do things like diagnose brain disorders, so things like epilepsy, strokes, or sleep disorders. They can also be used to do things like detect emotions or detect if the wearer of the EEG headset is focused or unfocused, or in our case, we were trying to detect attempted arm movements. So when we first started this project, we used a supervised learning approach where we would have a user wear the headset, and then they would close and open their hand based on instructions on the screen, and then we would save that data, and then we would use it to train a machine learning model. But we ran into a few problems with that, that it just didn't really work that well. There were quite a few problems with it. But then in NatHacks of last year, we saw a project by Karam Javed and Abhishek Naik, where they presented something called real-time learning, where in their setup, they had this like virtual dog that was walking on the screen, and based on moving their left or right eyebrow and wearing the EEG headset, it would turn left or right, and they could train it in real time. Within about a minute, they could have the dog learn to walk left or right based on the EEG signals. So we thought, why don't we take this setup, and instead of having a dog walking left or right, we have a hand that's trying to close or open. So reinforcement learning specifically refers to learning to predict a label for some input by receiving positive or negative feedback. So in our setup, we had a user wearing the EEG headset, and they would send these EEG signals into our reinforcement learning model. And then the reinforcement learning model would make a prediction of whether the user wanted to open or close the hand. And then it would show this prediction to the user, and then the user would either give it a thumbs up or give it a +1 reward by hitting an up arrow, or a -1 reward by hitting the down arrow. And over time, the reinforcement learning model would learn to correctly predict whether the user wanted to open or close their hand. So there are a few benefits over supervised learning that we found with this approach. The first was that the user could provide direct feedback to the model in real time. So each individual could train their own model that works how they want it to, rather than being told some instructions from a screen and then having that data train a machine learning model. You also only needed to provide samples until the model was trained. In the supervised learning setting, we record all the samples ahead of time, so we would have to sort of guess what's a good amount of samples to train a good model. And you just sit there closing and opening your hand, and sometimes we get more samples than we need, and it becomes really tiresome. But in this case, you train it until it's working, and then you can stop training, and then you save that model, and then you can use it to operate your prosthetic hand. And the last thing was we didn't really have to deal with issues related to user reaction time. So in the supervised setting, we would tell the user, okay, now close your hand, and then we would give them this 2-second period to open or close their hand. And the problem was we didn't know exactly when in the signal the user would close or open their hand, and it made it much harder to train the model. And with reinforcement learning, because they perform the action and then they immediately give the reward based on the reinforcement learning's prediction, it means you just deal with this reaction time in real time. So we took this framework and we ended up making a library called Hecatron, where a user can train this reinforcement learning model to predict the EEG signals with any action that they wanted. So there are 3 steps to using this library. So the first step is you connect your device, and we have this live plot where you can see that the EEG device is properly connected and reading signals in. This next step from there is to train the model. So the user gets to see the screen where they can see the predictions that the reinforcement learning agent is making, and then they can give these positive or negative signals, which are the red up and down spikes, and then over time, the reinforcement learning agent learns to correctly predict the signals. And then in the third step, you can use your model to basically take the actions that you've trained it to learn to predict. So in this case, we would assign a function to activate or deactivate the motor based on the reinforcement learning's prediction. So the library is publicly available if you are interested in checking it out. I have this QR code. I'll have it again at the end of the slides if you want to grab it. So what's the second project that I'm going to talk about? It's called fMRI-CLIP, and this project was done in collaboration with Jay Riley and Udwak Ituin for Compute 624 in fall of last year, which was instructed by Dr. Alana Fish and Dr. Alex Murphy. So the original goal of this project was that we wanted to develop a language model that could utilize brain recordings in training without requiring them in later use. So our goal was to basically improve the performance of a language model by using real human brain data, but we didn't want this brain data to become a requirement to use the model later on. What we ended up making, though, was a model that could predict associated text and fMRI scans of individuals reading that text by using contrastive learning. So first off, what is fMRI? fMRI stands for Functional Magnetic Resonance Imaging, and it refers to recording blood flow in the brain, which correlates with neuron activity. How is this different to EEG? Well, the first thing is the fMRI, as you can see in this picture, it's much larger than EEG headsets. So it's not something you can just walk around and wear on your head. It's this big device in a hospital or a research center that you have to go inside of. It does, however, provide much greater image detail. So with the EEG headsets that we were using, for example, the Muse headset, which is the band that goes around the front of the head, that only records four channels at a time. So each sample, you only get 4 different signals. Whereas with an fMRI scan, you get this big scan of the whole brain, which has thousands of voxels, which are 3D pixels. The downside, though, is that it takes a lot longer to capture these images. So with the EEG headsets, the ones we're using send about 125 samples per second, whereas fMRI scans take about like 1 to 2 seconds to record one image. There's also a delay in the observed response. So with EEG, if a user reacts to some stimulus, you see that response pretty shortly after, whereas fMRI, it takes about 5 to 6 seconds to see the response. So the fMRI text data set that we were working with, it was a data set from another paper that also worked with fMRI and perceived text. And it had the fMRI scans of 8 subjects that were reading Chapter 9 from Harry Potter and the Sorcerer's Stone. And the way they had it set up, they were in the fMRI machine, and they had this screen where they were shown each word for half a second, and then an fMRI scan would be taken every 2 seconds. So there were about 4 words associated with each fMRI scan. And then this was divided into 4 runs. So they would read for 11 minutes, and then they would take a break, and then they would read for another 11 minutes. So they read for 4 runs of 11 minutes each. So we wanted to, because the original goal was to improve a language model with fMRI data, we thought maybe we could do something with the embeddings, because language models are trained on embeddings. But what is an embedding? Well, an embedding is just a numerical representation of something that's typically not numerical. So, for example, words. It's a way to represent words as a vector. So there's a bunch of different ways to do this. This picture shows word2vec, which is an algorithm that generates these word embeddings that incorporate the meaning of that word by looking at how the word is used within different sentences. But what we ended up using was something called CLIP, which stands for Contrastive Language Image Pre-training. And what CLIP does is it produces text and image embeddings simultaneously, such that an image and its caption will have similar embeddings. So it uses contrastive learning to build these embeddings. So an image and its caption will have similar embeddings, and an image and unrelated captions will have dissimilar embeddings. So our original goal was to build these embeddings so that we had fMRI image embeddings that were trained alongside text embeddings, and then use that to train a language model. But there's another thing you can do with these embeddings, is that you can use them to identify matching images and captions. So once you've trained your CLIP model, what you can do is, let's say you want to predict a caption for some given image, what you can do is you can generate the embedding of that image, and then compare that image embedding with the text embedding of a bunch of possible captions, and then whichever one is most similar, you select as that caption. So in this case, the photo of a dog, you would compare that image embedding with, let's say, a photo of a plane, a photo of a car, a photo of a dog, and then in the end, a photo of the dog, the caption would be associated with that image. So what we wanted to do is we wanted to take the CLIP architecture, which is trained on images and text, And we wanted to change it so that it would instead be trained on this Harry Potter text that we had and these 3D images, these 3D fMRI scans. And then we could predict what text someone is reading just based on their fMRI scan, and we would also be able to predict what the fMRI scan looks like of someone that's reading some given text. So in this context, when I say encoding or decoding, for encoding, I mean predicting the brain response given a stimulus. So in this case, this is predicting the fMRI of an individual that's reading some text. And in the other direction, we have decoding, which is predicting the stimulus given some brain response. So predicting the text that someone has read just by looking at the fMRI scan. So how do we evaluate this model? How do we know if it's working like we hoped it would? Well, to evaluate it, we get this accuracy from doing this paired test, where what we would do is we would take our, for example, in a decoding setting, we would take our fMRI image and we would get the embedding of that, and then we would compare that fMRI image embedding with the text embedding from the ground truth caption, so the caption that was actually associated with that fMRI scan, and then we would also compare it with the text embedding from some random sample from another fMRI scan in the data set. And then if the image was most similar to the correct text embedding, then we would count that as a win, otherwise we would count it as a loss, and then we would perform this for all of the test samples in the data set, and then once we average it over all those, we get a total accuracy. And then we also evaluated the model using different context lengths, so different lengths of text samples. So we tested from given 4 words that they read versus given an excerpt of like 20 words. So the first experiment that we did with this was a within-subject evaluation. So we would train a model for each of the 8 subjects in the data set. So we would train the model on 3 of the 4 runs, and then we would test it on the run that the model had never seen before. So we're trying to predict based on data it had never seen before. And we would do this for each of the 8 subjects, and then we would average it over all those. And what we found is it didn't really work when we did within subject. So in this case, if you were just randomly guessing, you would get a 50% accuracy, and we found the model got just barely over 50% accuracy, and to the point where we could say it's not really learning anything for the most part. And we thought maybe the issue for this is that it just doesn't have enough samples. Each individual had about 1,000 fMRI and text samples, and we thought maybe this isn't enough to be able to predict what text someone's reading based on their fMRI scan. So what we instead did was this cross-subject evaluation. So in this setting, we would instead train one model on the data from 7 of the 8 subjects and just run 1 to 3 from each of those subjects. And then we would evaluate it on the left-out text from the left-out subject. So it was both brand new text and brand new fMRI data that the model hadn't seen before. And in this case, we found that the model actually seemed to work. We got about 69% decoding accuracy and about 74% encoding accuracy in the best case. So that was when we had, the more text we gave it, the more accurate it seemed to get. So it did seem like the issue was that it just didn't have enough fMRI data. So once we increased that, we got better results, and it seemed like the project worked in some way. And the data set we were working with was pretty small, so the hope would be if we then tried it again with an even larger data set, that maybe we could get even better results. And those are the 2 projects that I wanted to talk about that involved both machine learning and neurotechnology. So thanks for listening. Q&A? Just, you're going to have to do that. Oh, take them off. Yeah. Yeah. I thought that's what we're doing. Anything I would say would just be just a random guess, I think. But more than 8, I guess. Yeah. So the data set that we chose was because, well, at least from the research we did, that was sort of the most fitting data set for the problem, because we needed something that had both fMRI and text data and was publicly available, because we only had so much time to do the project. And we had also read the paper that the data set came from. So sort of all those was the reason we chose the data set. Yep. I don't think we would be able to get 100% because there's noise in the fMRI scanners. There's also, I imagine there would be multiple, well, if you had enough text data, there would be multiple sentences that got very similar responses from the brain. In our case, we were doing, because we did this paired test, maybe we could get sort of close to 100%, because there's maybe a good chance that the random sample you grab is a completely different text sample and wouldn't elicit a similar response. But if we were doing something and we were just directly trying to predict the text that they read, I don't think we would be able to get near 100% accuracy. Yep. Yes, so there's quite a few other papers that have done a similar thing with using CLIP and fMRI images, but they instead of having red text, it's images that the individual looked at, and then it would be trying to predict, based on the fMRI scan, what image did they look at. There's some papers where they were able to recreate the image that an individual looked at just through the fMRI scan. So there's a lot of good work with that. From what we had seen, we didn't really find any papers that had used the CLIP architecture to predict text, but yeah, there's a lot of like image-related ones. All right, I think that's everything. All right, thank you.
Before we introduce our next speaker, I would like to inform you guys a bit more about some other events hosted by Neurotech, including but not limited to workshop sessions, future natChats, and of course, one of the biggest hackathons in all of Alberta, NatHacks, that has a prize pool of over $30,000. We invite everyone to join us in our future events and spread the word to your peers. And now, for our today's keynote speaker. He is an exceptional person who is working towards integrating brain data and into machine learning models for language and vision. Being an AMI postdoctoral fellow at the University of Alberta, their expertise in natural language processing and cognitive neuroimaging pushes them to explore the enhancement of machine learning models through human language processing. They are an important part of the Neurotech ecosystem, pushing its boundaries, all the while bridging the gap between neuroscience and AI. Let's all give it up and welcome Dr. Alex Murphy for his presentation.
Testing. Testing.
You need both of them? One of them is recording, and the other one is for the speakers.
Okay. My name is Alex. I'm a postdoc in the lab of Dr. Alana Fish. Together we study the intersection of cognitive neuroscience and machine learning, specifically trying to learn about the brain through AI methods as well as trying to learn novel ways to study machine learning and develop the next generation of algorithms by incorporating brain data into the modeling pipeline. So I'm also we're funded by Amy, which is one of Canada's 3 AI superclusters, as you probably know, and we have Mila in Montreal and Vector Institute in Toronto. So what I'm going to talk about today is the topic of foundation models and kind of a perspective talk on where I think the future is going to be and where we're going to step into, and just kind of prime everyone for what I think is on the horizon with regard to AI in neurotech, through looking at where we were with older style machine learning models, the path the foundation models took in the general AI setting, so with vision and language models that we've seen. And then what underlies those is the concept of scaling laws and just how much can we expect models to do better if we scale up the amount of data that we put into these models. And then I'll switch to explaining a few potential applications of how you might want to use foundation models for BCI applications, and then linking other ways to link brain data with foundation models, and again, thoughts on the future. So what we used to have in machine learning would be that you had a problem that you wanted to solve, you had a task that you wanted to learn about, and you had a specific data set, and you would learn a model on that training data set in order to do a specific task. And every new task required a new set of training data, and these models were all kind of individual, but pretty soon afterwards, it became obvious that, say, what unites all of text modeling or text tasks like spam classification or sentiment classification, or in vision models, for example, a lot of vision models that have different end tasks require a model that can detect the presence of objects in images. So the concept there that there should be some of the early layers, and I'll demonstrate this with an example on convolutional neural networks and exactly how this works. So if you wanted to do anything to do with images recently, until a few years ago, you would use a convolutional neural network model, which is basically just a mapping of layers from an input to an output, where you have to learn, or the model will pick up features of an images, and the convolutional filters in each layer would gradually be trained in a way to detect things going on in images that help it solve its actual task. And so if you were to take a model that's been trained and then look at, say, the early layers of, so close to the input stage, you can see that there's what's learned as orientations of specific lines and color patches and very, very basic images, it's very basic properties of images that are then developed in the middle layers of a convolutional neural network, where, say, if you want to detect like a joint, you would take the representations from the early layers and you slowly build up levels of abstraction and complexity until you get to the late layers, which are more task specific. So I'm not sure how well you can see it, but at least the bottom row of this late layers one, this is a filter that's learned to recognize a bird with a long beak, for example. So what we can say about how this model was trained would be the model has found it useful to be able to detect animals in images, and that has been what it's trained on. So those later layers are task specific for, say, object recognition, but for all different types of visual tasks, most models would need to be able to model basic shape information and how that develops in these, say, early and mid layers. So if you have 3 tasks here, rather than train them individually, it makes more sense to have one model and then have 3 task-specific layers. Then you get to have 3 times the amount of data, and then those shared layers would have more representations or more examples to learn from. So the early layers are trained better, and therefore you also lead to better task-specific models. And so the analogy here with humans is like, if you already know Spanish and you want to learn Italian, that's nowhere near as difficult as, you know, turning up to your Japanese lesson if you have never seen a Japanese character and have never heard the language before. You know, one is like what we call like a cold start. You know, you know nothing. It's like a random initialization, and the model has to learn everything from scratch. Whereas in the case of the Spanish speaker who wants to learn Italian, for example, you really have a lot of the baselines already present, and you just need to kind of know, you know the idea of how the syntax will work, the word order, and things like this. And perhaps like another useful way to think about this is like with learning a musical instrument. So if you're a piano player, for example, and you want to learn how to play the saxophone, you already benefit from the fact that if you have good rhythm, you can read music, you have a well-tuned ear, you know things about scales. Whereas if you just pick up an instrument for the first time, you have all that to learn, as well as the technicalities of the instrument itself. So this was how things were, where we were trained with supervised learning with inputs and outputs and labels that would give the supervision to the model. And we're just going to jump forward a bit to the secret sauce of how a lot of, basically all of the big machine learning algorithms that you have heard of today. And they're all trained by this method called self-supervised learning, which this is Jan LeCun, the lead AI researcher at Meta, who has called this the dark matter of intelligence. And so what this is taking the input and creating a label from that. So this is why it's called self-supervised learning. So if you have a sentence, you can randomly delete a word in the middle and use this as the label and say, with the numerical representations that we have for these other words around it, what is the prediction for what this middle element should be? And also for images, how we can conceptualize this is you can take an image and you can randomly sample, distort it, maybe flip it vertically, invert the colors or something, and use the same model to map the representations to a different numerical space and then make sure that they match. And it's all about learning the image statistics or the text statistics. So self-supervised learning is basically the idea of take the properties of the input data itself and just learn what actually commonly occurs in there. And this is then the secret sauce, the dark matter of intelligence, that starts a model in a much better place in order to then be trained for specific downstream tasks. Here's another example for how this is done with fMRI, for example. So then we move to the stage of you can have gigantic amounts of text, or you can consider the whole internet of text, and then you would run a self-supervised learning model on what we'd call like a pre-text task or pre-training, and then this would learn all of the general representations in a self-supervised learning way, and then you would use these representations to then do supervised fine-tuning. So the concept is learn the properties and the statistics of the data, and that's much better than going from a random initialization straight to learning a model on a specific downstream task. So what was happening in this earlier stage was, we would have a model for language, and then we'd have a model for images, for speech. Then the model started to get even bigger and bigger, and people started to think, okay, what if we included text, images, speech, structured data, 3D signals, and put them all into the same model? And all of them have their own self-supervised learning training objectives, but they all go through the same shared representational space. And this can then be derived to fine-tuning and adapt the model in order to do many, many, many different tasks. And the idea is that the overlapping representations across all these different modalities is just helping the model have a better formulation of, what are the properties of this world that we live in and the things that we want to model and the intersection between all of those. And this is sort of where we are now with large language models and vision language models, and how you can upload an image to ChatGPT and ask you for a description. And it's all because this is co-training of multiple modalities in the same thing. That is what was going on in the world of AI. And then on the peripheries of science, as you can imagine, then people started to say, okay, well, how can we apply this to some of these more specialized cases, like, for example, with the brain? And so one way that you can imagine a foundation model for the brain would look like would be to repeat the same process, perhaps by having many, many examples of EEG data, or what I've used here to say fMRI, or it could be any sort of intracranial recording, basically like before with the images and text across many different domains. Have a model that just learns what does brain data look like in the ways that we use it. So you can provide it with hundreds of thousands of spectrogram derived from EEG signals, or actually model the waves. And the idea of using self-supervised learning would be to delete some part of the middle and say, given everything else that's going on, predict the middle and learn the statistics of what's going on here. And this foundation model would then have a very, very good idea of what all sorts of different types of brain data would look like. I don't have enough time to go through many of these other papers that have started to propose foundation models for EEG, but there are one or two that I would like to highlight here. So, for example, this NeuroGPT model is quite a good example of exactly how to apply this foundation model idea to more of a BCI setting. So, as you can see in the abstract here, basically the point is they would take large segments of EEG data, they would mask out a middle section, and they would train the model to say, given time before this and time after this, what is actually going on in here in the middle, and predict the representations and learn the statistics of the EEG model. Then they looked at a motor imagery classification task, where they had about limited data from about 9 different subjects, so people imagining moving their left arm, the right arm, the legs, whatever that was. And once you would hook up that data via a foundation model and then tune it to your outputs, that model, obviously, according to the theory, and this was borne out in the data, performs much better than taking the original 9 subjects and just trying to do motor imagery classification in the traditional way, as was done before. There are further ones here. I won't go to. This one is magnetoencephalography and doing brain to text via the throwing in OpenAI's Whisper model, which is a foundation model, but actually specifically only for speech. And so basically the idea of foundation models is what has been called sort of the scaling laws. So, with images and language, a lot of people have done many different calculations and said, okay, if we have the same model and we just ramp up the amount of data that we give to the model, the performance metrics will carry on increasing, but maybe up to a certain point. But this hasn't really been explored in any application for the brain. And so in the middle of July, so just a few months ago now, this paper came out. It really kind of surprised a lot of people who had not expected to get such good results with this. So there is still a degree of skepticism about this because it hasn't been replicated yet. But just to take some tweets from one of the authors in here who kind of categorized the context of what this paper means and their contributions to the field, where they say, we discovered the scaling law by pushing this non-invasive EEG using ultra-high density, I think it was like 300 or 400 electrodes in the ultra-high density setup, and then collected 175 hours of EEG, which is, if you work with EEG data, that's a huge amount from a single subject. And so this final tweet here, the scaling law was previously unknown because it's not common to collect data from a single subject, but I think prior to this, with non-invasive EEG, to get the results that they claim that they have shows that the scaling law, we are nowhere near hitting the ceiling. And this bodes well for the idea of using foundation models in BCI and in Neurotech because if it is just the case that we require extensive data collection, which we can possibly get by artificial sampling and data augmentation techniques as well, that there is plenty of scope to start using these models more commonly. And so we don't really need to see the exact models, but here, as you can see, as the data set size increases from left to right in each of these figures, the performance metric will increase. And there's no new training technique. It's just a case of having access to more data and training a bit longer. That this does seem to be the key from going from bad results, which nobody would really know. So from the levels of data that had typically been applied until a few years ago, you probably class a model as this is not even working to do anywhere near as well as what these authors have found. So there is something to the idea of using scaling and increasing the amount of data that your model has access to. So there's a company called Pyramidal, and they put out a press release only about 2 weeks ago, and they are building a foundation model for EEG. And there's one quote in there that I thought was quite a good description of backing up this point of where we are going in terms of foundation models for BCI applications. And they say, there's no world where a model trained from scratch will do any better than a pre-trained model like ours, and having a warm start can only improve things. So the concept of warm start is like this Spanish speaker learning Italian, for example. You have a lot of the basis information already, and it's just a case of tuning slightly for your specific applications that you want to model. So if we go back to some fun case of how this might be applied, we probably know, or have seen some of these EEG-controlled helicopters from about 5-10 years ago. And on the right is sort of the pipeline of how the system might work. So you take your brain activity in terms of the raw EEG signals, do some basic signal processing on them, and then generate a spectrogram. And I've put in here the foundation model in here. So rather than doing this all from scratch, if you imagine that there's a foundation model that has seen hundreds of thousands, maybe even millions of spectrograms like this before. So typically, if you wanted to control, say, a direction to go left, right, up or down, a common way to use a BCI application would be to do motor imagery. And so you would say, if you imagine lifting your left hand or right hand, they correspond to different directions. Same with legs, left leg, right leg. And instead of having a model trained from scratch, have to detect, okay, what is this data format that's coming in? I've never seen anything like this now, and I have to figure out how to model spectrogram data, as well as figure out this whole left to right thing. If you already start from a model that knows everything about human responses and spectrograms, as soon as it sees this input data, it's able to say, like, I don't have a label for this just yet, but I know enough that this all looks like it belongs to the same class here and the same class here. All I have to really do is associate an output label of left to right. And by doing that, the benefits that can be conveyed through using foundation models are the fact that you can generalize well, you can use transfer learning in order to do slightly different tasks. But one of the key ones that I think is important here is the idea of robustness. So like if you were to try to repeat your experiment, but let's say you put your EEG cap on and some of the electrodes were placed slightly differently, you're going to be recording from a different population of neurons. And a model trained from scratch hasn't seen any of that before, so it might just think, I've never seen this type of data before. It's different from what I'm used to. I really don't know how to deal with this. Whereas a foundation model that's seen hundreds of hours of brain data beforehand would have a pretty good idea to be able to associate it to what is already known in the model and be robust to things like user fatigue and slight placement, and maybe be able to adapt better from between participants. So models won't have to be, say, subject specific. You could actually have something a bit more general, as well as the ability to have more complex pattern recognition. So it's fairly crude to imagine, left hand, right hand motor imagery, left leg, right leg. If you have a system that's so able to have access to a lot of this data, you might be able to think, okay, could the model actually start to detect different finger movements? So instead of only having access to 4 commands via, moving the forelimbs, maybe you could have access to much finer grain commands by, a model is able to detect that you're moving a thumb versus a finger on your hand. we're really kind of just taking that first step into seeing what's possible with all of this. So that idea of foundation model was actually having a model trained on brain data in order to know what brain data looks like. But there is another way that you can bring foundation models into potential BCI technologies and in Neurotech. And that idea is if you have a brain response to a stimulus, and that stimulus is, say, an image, and you can put the image through a foundation model, like a CLIP, like Harrison spoke about, then you get a very rich representation, and with limited brain data, you can learn a linear mapping that goes from brain data to predict what's going on in the representational space of the foundation model. And then you can take a ton of different images for which you don't have any brain data and put those into the same representational space and start to figure out a lot of really interesting things and discover new fine-grained concepts of what's going on in the brain. So we recently submitted a paper where this is kind of it's a 3D brain view from fMRI, and you can click around and see these different patches. So one of these patches you can click and you can say, okay, in this other giant data set, what are the images in this foundation model that are really in the cluster, very, very close to what we can detect here? And we can see, okay, so there is a pattern here. So if we click into this part, so there's like these three red axes that delineate exactly where in the brain we're pinpointing, but these all seem to be responsive to very colorful food images, whereas if you click into a different part of the brain, then what's responsive here is many, many different images of people who, sorry, not just individual people, but it specifically seems to be sensitive to crowds of people in different types of settings. So going beyond what was decodable from the brain originally, which might have just been, say, cat versus dog versus person, you can actually start to get way more fine-grained information from linking brain data to foundation models in a way that's different from actually modeling the brain data directly, which is another possibility. So to wrap up the main points, collecting data is difficult and expensive, and especially so in this low data regime of typical BCI and sort of in the hobby settings. But if you want to use foundation models, you would probably see a lot of benefit in there. But as of yet, a lot of these large-scale data sets are kind of within research labs. They're not open source, or like with this pyramidal company, data is key nowadays, and it will take time for things to come out into the open to be open source. But once we're there, and I don't think it's going to be too long, perhaps a few months, maybe 6 months, that we will have kind of crossed over into this threshold where you will never train a model from scratch again. You will always want to use a foundation model or something that's been pre-trained on a lot of generic data using a self-supervised learning mechanism. And so that's not to say that it will happen immediately, but I think that pretty soon we will have solved this, and this will be ways where people will start to see huge jumps in accuracy and the ability to do some much more interesting things with BCI that kind of haven't been seen beforehand. I did try really hard to see if there had been any kind of release of brain-computer interface foundation models or things, and the closest I found was this Neurotech GitHub repo, and they just have a coming soon and working on this, check back later. So I think that now the signals are all there that it's not really possible just yet, but I think that if you're primed to expect that this is going to arrive very, very soon, then you could actually be in a really, really good place if you do intend to develop BCI models and a lot of other interesting things. So I would say practical tips of think about how you might apply this to your own problems. And let's say you might have tried 10 different BCI experiments in the past, and they've never really worked, but you still have that data saved somewhere on your hard drive. That is not maybe useless data. If you could come up with a way to do self-supervised learning on that, maybe to learn the specifics of your brain activity, then you could then have a smaller foundation. Well, it wouldn't be a foundation model, but it would be a generic model that's not starting from a random initialization. And then that could be the key to adding extra data in order to help you actually do, or say the experiments that you thought had failed might actually work if you can collect enough data and do some random sampling and data augmentation techniques that we're still sort of not 100% sure how much you can get out of that, if they will work or not. And yeah, so I just have two small book recommendations. If you are interested, then this new mind reader is more based on decoding of MRI, and it's very much for the lay audience, but it's extremely interesting. But I wanted to give a highlight to this book on the left, The Battle for Your Brain. So I've been interested in BCI for a while, and I had no idea of the extent to which neurotech is actually being applied in different regions of the world. So, say for example, truck drivers are mandated to have EEG sensors, and if they're detected to become too fatigued, then there's a signal sent to the company that would say that you actually have to stop driving now, and some of this thing that is going on, and I think a lot of people might not realize it, but if you are interested in any of that and the ethical issues that happen, say as foundation models will come in to boost the applicability of a lot of neurotechnology, I think the ethical issues are only going to get more and more prominent, so it's quite an interesting read. So if there is anything in my talk today that you want to use, and or maybe you have an idea but you're not sure exactly how to go about it and you want to run a few ideas by me, this is my contact email address, and I'd be happy to hear from you, and that's the end of my talk. Thank you. Any questions? Yeah.
So you had a quote from your CEO saying you're always the best start. Do you agree with that? Like I feel like if you had maybe you train a model for one specific individual or wearing one specific headset, is it helpful to include all the data from other people that have headsets with different numbers of sensors?
I think in comparison to actually just being a random model that has no idea of the structure, so it's about, like with the example of the CNN filters as well, all those models need to know about the basic shapes and how they interact in order to then do more complex classification tasks at the end. And I think that if you are restricted to a certain data that looks a very specific way, so from a random initialization, you can basically model anything, or as long as you have enough non-linearities and parameters in the model, that I do think that it's not really going to be the case that having something that's less random and more in the style of the data that you will be feeding to the model, I can't ever see that being worse than random. So I would agree that that start of at least having a signal in the model for how to develop it, it doesn't have to go from, because I would say that a model trained from scratch to do those tasks on that different data set would still need to know and learn all of those statistics that are already present, like in a generic way in that model. So it's kind of just taking on the difficult part, and the updates that you can do are much fewer, and you can do more with fewer data points in that case, yeah. I actually hadn't thought about this whole plasticity loss in RL that's all the rage recently here. I don't see how it could hurt. I think that it's not taking the model to a place that's going to be detrimental to its final task. I think if it's not useful, it's not useful, but being able to kind of know what data it's not like would always help there. So in that case, it might just be that starting from random scratch and going there, you're not going to have a more difficult job to, with this plasticity stability dilemma by using a foundation model pre-trained to know the data type at least. I mean, it could be beneficial, I think. I have to think about that a bit more. Yeah?
So we saw in the slide where you were showing how specific tasks could be had, like let's say, two images with associated or people images.
Yeah.
Is there ever a possibility that it might be connected to emotion? Like, let's say one part of all happy images or more sad images. So, or is it just that it plays upon
That information could theoretically be there. I don't think that's very easy to investigate because it's quite difficult to get at that, whereas one of the benefits of using these foundation models is the fact that it's trained on images, specifically on the image statistics, and that's what you're actually learning. But it is quite feasible that the brain response, in a way, while being able to be linked to these images, also has the activity there to be able to model it. But typically what we do when we do those experiments is we restrict to kind of the visual cortex of the brain and those responses, and they're not typically areas that respond to images. But if you were to go to like a whole brain analysis where you include parts of the brain like the amygdala or other areas of the brain that are more connected to emotion, then there is that idea that could be possible to detect and explore. But typically in the way things are done now, you kind of restrict to the brain, the areas of the brain that are responsive to the types of images, or say speech and the temporal lobes. Yeah. Yeah.
Where do you see what applications do you see foundation models being used in specific
I would say there's not really an application, or if there's currently a desire to do something with Neurotech at the moment. I can't see a place where it wouldn't be appropriate, because the idea is that if that definition is also there, I think it's more of the case of stuff that people didn't think would be possible with only a limited amount of data. It can only really expand the possibilities of, okay, so maybe we don't have to, a model could not learn something so complex, but if it obviously has this warm start, then I think I would just see that there's more applications outside of what's typically considered possible. So there's not really an area that I think would be specifically associated more than any other. I think it's just goes along with the reason why you would have the Neurotech application on in the first place. So. Yeah, that's everything. Thank you.
Thank you both. Thank you both, Dr. Murphy and Mr. Fah, for sharing with us your research and insights. Now, I would like to invite you to the front of the hall, because we want to extend a very heartfelt welcome and present to you a token of appreciation from the entirety of Neurotech. Devote their time in attending the event, and hope that you were able to expand your knowledge on AI and neurotechnology through it. We would also like to thank our sponsors, without whom this event would not have been possible. And we encourage everyone to please fill out the feedback form for the event, as there is a chance to win a $40 gift prize, and you can access the form through the QR code on the scene. And now we invite everyone to take refreshments and engage with each other and open the floor to networking. Thank you so much.